Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last lecture we laid the foundation for logistic regression, which is one of the simplest ways to solve a binary classification problem. So if we have to develop a classifier that can discriminate between two sets of classes based on a set of features, a logistic regression is one way to do it, and it relies on the logistic function, which is a type of a sigmoid function that is used to assign the probability of the target variable being 1, right. And the target variable is a binary variable. If we predict it to be 0, then you are in class 1, and if you predict it to be 1, then you are in class 2. So that is how the logistic regression method works, and we had also discussed one way to understand how well a logistic regression works, and that was the confusion matrix. And in terms of mathematical ways to quantify the accuracy, we had looked at the balanced accuracy score, which is very important for imbalanced data sets, and then we had discussed things like the sensitivity and the specificity. So in today's class what we will do is we will go forward and understand another metric known as the receiver operating characteristic area under the curve. So short formed as ROC AUC. We will understand how this particular metric or the ROC plot by itself is useful, and then once we finish that we will continue on to the discussion of softmax regression, which allows us to generalize the logistic regression to a multi-class classification problem. So let us go ahead and get started. So we want to study the concept of the receiver operating characteristic ROC, right. And like I said, this is one of the ways to understand how well the binary classifier that we have developed is performing, right. So it is one of the ways, and then like I said we had already been introduced to other ways, and these include the confusion matrix and the balance accuracy score. Okay. So the receiver operating characteristic ROC is a plot in which what you do is you plot the true positive rate TPR versus the false positive rate. FPR. Okay. And this plot, right, is done for various values of the classification threshold probability. Which we had denoted in the previous class as P star, right. If you remember, the logistic function predicts the probability of the class being 1, right, y equal to 1 or class 2, and then this probability needs to be beyond a certain threshold for us to classify it as belonging to that particular class, right. So this threshold property is a very important number, and that determines how we assign, right, the target variable. So the predicted value of the class y hat, right, this is equal to 1 if your predicted probability by the logistic function is greater than equal to p star, and this is 0 if p is less than p star, right. So this is what we learnt in the last class, and then y hat equals 1, that tells you that you predicted the second class, and y hat equal to 0, that means the predicted class is the first class, right. So this is how the classifier works, and just to refresh your memory, the p comes from your logistic function, right, which is a sigmoid function that varies smoothly between 0 and 1, right. So now what will happen if we plot the false positive rate versus the true positive rate versus the false positive rate? Let us see how this works. Okay. So just to refresh your memory, the true positive rate TPR is equal to the true positives divided by the true positives plus the false negatives, right, things that were wrongly classified as negative, and the false positive rate is equal to the false positive divided by false positive plus the true negative. Okay. So this is the false positive rate. Now what will happen as we vary this threshold probability, right. So we are trying to vary the threshold probability p star, and then we are plotting the TPR versus the FPR, right, and this variation goes from 0 to 1, right. So we are varying p star from 1 to 0 and plotting the TPR versus the FPR. This is what is basically the receiver operating characteristic, right, and you can read at other places why exactly it is called a receiver operating characteristic. There is some interesting trivia behind this. Okay. So let us try to vary p star from 1 to 0 and see what happens. So when your p star equals 1, right, so this particular threshold probability is too high. Remember this particular formulation, your predicted probability has to be greater than equal to p star for us to assign y hat equal to 1, right. So when p star equal to 1, right, it will be impossible, right, for this p to be greater than equal to p star, and therefore, right, all y hats will be assigned 0, right. So if you assign y hat to 0, you can never predict any sample to be positive, right. So no sample can be predicted to be positive. So your true positive rate will be exactly 0, and your false positive rate will also be 0. This is because, like I said, the threshold is set to a too high value, and therefore no class or no point will be classified as positive, right. So both TP equal to FP equal to 0. So this is what happens when p star equal to 1, and then you can consider the other sort of boundary case when p star equals 0. In this case, what will happen according to the equation above? Let us scroll up, right. In this case, your p star equal to 0, so all the points, right, will satisfy this condition, because obviously the probability predicted will always be greater than or equal to 0, right. So that is what will happen, right. So when p star equals to 0, all the points will be classified as positive. So even the points that are correctly classified, the true positive rate will be 1, and even the points that are incorrectly classified as positive, that will also be 1, right. So, both TPR and FPR is 1, since all points will be classified as positive. Okay. So, in this case both your true negative and false negative will be 0, none of the points will be predicted to be negative, right. So, now we have the boundary cases. So, when P star is 0, TPR is equal to 0 and FPR equals 0, and the other cases when P star equals 0, both TPR and FPR are equal to 1. So, let us go ahead and plot this now. Okay. So, I am going to plot, as I promised, the TPR on the vertical axis as a function of FPR, and this obviously will be bounded, right, by the square, because the maximum value of the TPR is 1 and the minimum value is 0, and similarly the maximum value of the FPR is also 1 and its minimum value is equal to 0. Alright, and we have already found out that when P star equal to 1, this is where the point will lie 0 0, and then when P star equal to 0, this is where our point will lie, right. So, this is the start point, the start of the ROC, and this is the end of the ROC curve, right. So, we know the starting and the ending points. Now, let us see what will happen, right. Now, if you take a perfect model, so for a perfect model, a model that is exceptional, right, it will always do the right thing. So, the true positive rate will be equal to 1 and your false positive rate will be equal to 0 for any classification threshold, right. If you had a perfect model, no matter the threshold you would give it, right, it will always predict points correctly. So, TPR will be 1 and FPR will be equal to 0. So, how will this look, right? The moment you even slightly increase the threshold, right, the ROC curve will jump here, and then this is how the perfect model's ROC will look, right. So, this is the ROC curve of a perfect model. Okay. And a random sort of model, right, a model that just guesses, right, will be like this, right. This is a completely random model. So, at any threshold, right, you will have only a 50% chance of getting the true positive outcome, right, and your false positive will also be 50% because it is a completely random model, and therefore, it will trace the y equal to x line, right. Now, any real model, right, if you now graph on this real model, it is going to look something like this. Let us choose this color. So, a real model may look something like this, right, it goes up and then it saturates, and finally, of course, it has to reach the end of the ROC curve, right. So, this is a real model. So, we have seen how the ROC curves look for a perfect model, for a real model, and for a completely random model, right. And now you can see that if you choose a different value of the classification threshold, you will get different values of the true positive rate and different values of the false positive rate, right. So, you can sort of use that to decide what classification threshold you want to use, right. So, for a real model, right. the ROC can be used to choose the threshold P star based on the trade off between the true positive rate and the false positive rate, right. There are costs of predicting a true positive and there are there are costs of predicting false positive. So, obviously you want to minimize it, but there are cases in which it may be little bit less it may be less problematic to have a false positive, but you really want your true positives to be correct. So, that is how this trade off can be used to choose the value of P star, right. So, this is about the receiver operating characteristic. However, there is a metric known as the area under the ROC curve, which is actually threshold independent, right. So, now we will look at this area under the curve metric. So, that is often shortened as AUC. So, the area under the curve AUC for a receiver operating characteristic so that we had shortened as ROC is a threshold independent metric to assess the quality of a binary classification model. Right. Now, because it is a metric, right, we have to understand what are the possible values of this metric, right. So, what is the area under the curve AUC under the receiver operating characteristic curve for a perfect model? So, if you go back to the ROC curve, you see that the receiver operating characteristic for a perfect model is essentially a curve that starts at the point 0 0, but then immediately jumps up to y equals 1 or TPR equals 1. So, if you found the area under the curve, that is this entire square region, right, the entire square region that is bounded by the arrows I have just drawn, that area is obviously 1 times 1, 1 is the side of the square. So, that particular area is exactly 1. So, the AOC RUC for a perfect model is equal to the number 1, whereas the AUC ROC for a completely random model is, as you may have rightly guessed, 0.5, right, because that is the area in this particular region, that is the area under the ROC for a completely random model, and the area of that triangle, half base times height, is half times 1 times 1, and that is certainly 0.5, right. So, therefore, typically a real model will have the AUC ROC between 0.5 to 1, and the closer it is to 1, the better it is, right. So, this is how the receiver operating characteristic curve works, and this is how, right, the area under the curve is a useful manner in which we can understand, right, how these models are performed. Okay. So, this brings me to the end of the discussion on your binary classification problem. Like I said, we will now go on from binary classification to a multi-class classification problem. So, let us go ahead and see how this can be done. So, the next topic that we are going to cover is multi-class classification. Right, and the way in which we are going to do this is called softmax regression or multinomial logistic regression. Right. So, just like binary classification was done with simple logistic regression, now we are going to discuss multi-class classification, which is achieved via multinomial logistic regression or softmax regression. Okay. So, in this case, instead of using the softmax function, instead of using the logistic function, we use the softmax function, right. So, the probabilities of the classes are evaluated using the softmax function, right, instead of the logistic function which we had used for binary classification. So, this function looks like follows. So, the probability that y is equal to k given the feature vector x, right, and this k is basically the index for the classes that we have considered. This is given as the exponential of beta naught k plus beta k transpose times x divided by the sum over all the classes j equals 1 through capital K e to the beta naught k plus beta k transpose x. Okay. And like I said, this k, capital K, is the total number of classes, while the lowercase k is an index for the classes. Now, these betas, as you rightly guessed, one of them is just a number, this is a vector, right. These are the parameters of the softmax regression ML model, right. So, this is how it looks. The nice thing is that this function obviously will lie between 0 and 1, right, because it is an exponential function, right. Exponential function always gives a positive value, and the exponential function divided by sum over that exponential functions and others for other classes. So, obviously this probability will lie between 0 to 1, and then you are going to have these features beta naught and beta k vector. Those features will exist for every class, right, and they have to be trained during the training of the ML model, right. Now, that is how the predictor function works, and you will select the class which typically has the highest probability, right, instead of what we did in logistic regression, wherein we chose the second class if your predicted probability was greater than 0.5. Here the strategy is slightly different. The strategy is that the predicted value of y hat to the largest predicted P. So, if you wanted to write it down, you would say y hat of the feature vector x is argmax over k p y equals k given the feature vector x, right. So, this is why logistic regression works, softmax regression works, and you are able to assign the correct class. Now, what is the loss function that is used here? In the case of logistic regression, we use the binary cross entropy loss. Here the loss function used is the categorical cross entropy loss. Which looks as follows. The loss function is a sum over all the data points and over all the classes, k equals 1 to capital K, and it is equal to minus I yi equals k log p yi equals k given the xi vector. Okay, so, this is how the categorical cross entropy loss looks like, and here this I is basically an indicator function. So, I yi equals k is 1 if yi equal to k and it is 0 otherwise. So, if the point I, right, really belongs to the kth class, then the indicator function is 1 and it is 0 otherwise. Now, one can show that this particular loss function, right, reduces to your binary cross entropy loss function for logistic regression if you consider only 2 classes. Okay. So, with this I hope you have got a nice introduction to softmax regression as a segue from the logistic regression which we had covered in the previous lectures. Before ending, I just want to list some examples of where a classification problem may be used in the core engineering disciplines. Of course, these are just the tip of the iceberg, and I encourage you to think a little bit more about how classification can be useful in your discipline. So, here are some example applications. I have tried to derive them from various branches, but you would of course be the best judge of whether it is useful for you. So, this is what someone in mechanical engineering, right, may find it useful for example, fault diagnosis in machinery, right. You want to find out what is the type of the fault that has happened based on various sort of operating parameters and running conditions of a machine, right, or you may want to understand, right, the failure detection in a component, right. So, there may be a component, right, in a certain system and you want to detect whether it has failed or not, again based on various operating conditions and process parameters. In the realm of civil engineering, one potential example is soil type classification. Let us say you have made measurements pertaining to the properties of a soil, you may have photos as well, and with that you want to classify what type of soil it is, and the other can be structural health monitoring. So, if you have a large bridge, right, or a large structure that you want to know whether it is safe or not, then you can have again an ML model based on various types of measurements of what the dimensions are, right, and what they currently are. So, that is something in civil engineering. In aerospace engineering, things could be slightly different. You may want to detect a fault in an aircraft. There are so many lights in a cockpit, right, that tell us, I mean, what is working properly, what is not. So, it could be like a usual regular intelligence, but one may also be using AI these days in doing that. And then there could be something like a landing success classification, right. Let us say you are making a drone or a flying object and you want to detect whether it has landed or not, that could be based on a classification ML model. Okay, so that is aerospace engineering. The next example I want to give is from chemical engineering. So, in chemical engineering, one may want to detect an anomaly in a process, right. So, let us say you have a process to produce a chemical and you want to detect whether it is working fine or there is some problem somewhere in the process. So, an ML model could be developed. The other is, let us say, a catalyst deactivation prediction. So, you have a reactor where a catalyst is being used and then over time it may get deactivated, it may lose its efficiency. So, you want to detect and understand, right, whether it has really happened or not. So, that could be an example in industry in chemical engineering. Now, moving forward, I have also taken some examples from industrial engineering. Right here, one may want to understand, right, whether the things being produced in a production line have the right quality or not. So, quality control check in a production line, whether your product has the desired attributes or not, or there is something amiss. And the other can be predictive maintenance. So, let us say your model is able to predict when your plant or your setup or device has to undergo maintenance, and again you can classify, right, whether you need maintenance or not. And finally, I want to take one example from environmental engineering, right, which is also very relevant, and this pertains to pollution levels in the environment. So, in the realm of environmental engineering, right, you may want to detect the water quality, right. So, water potability detection, whether the water is fit to be drunk or not, right, safely by humans. And then similarly you could have air pollutant, right. In all these cases, depending on whether it is required or not, one can also think of regression problems. For example, if the classification model does tell there is a pollutant, then you can try to understand what is the concentration of that pollutant. Similarly, here we can understand the concentration of salt in the water or other types of things, and so on and so forth. Alright, so this brings me to the end of this particular lecture in this course. I hope you got a good feel of the receiver operating characteristic used to understand the performance of a binary classification model, and how the area under the curve allows you to understand the performance of the binary classifier. Next, we discussed the concept of softmax regression, wherein we generalized how we can go from binary classification to multi-class classification using the softmax function, which is essentially a normalized exponential function that tells a probability between 0 and 1 for various classes, and then we pick the class with the highest probability. And finally, I told you examples of various problems from different core engineering disciplines where you could find utility of classification problems. I hope you learned something in today's lecture. Thank you for joining, and I look forward to seeing you next time.